we launch the program Gauss View with a double click. Then 2 windows appear. One is gray and has all the controls on it. The second one, which is blue or purple by default, is empty. This is where we will build our molecule. Now we will build the ammonia molecule NH3. For this, we use the control palette. Find the symbol with the carbon on it and click on it. Now the periodic table of elements will open. We choose N for nitrogen. And we also select the nitrogen fragment. In our case, we select the tetrahedral one. Now, we go to our purple empty window and click on it. Our molecule appears. In order to not make any unwanted changes, we use this symbol, which is a ruler with a question mark in front. This avoids that we can make any changes to the molecule. Now we can turn the molecule. We can also enlarge it by scrolling on the mouse. Now you can get familiar with your molecule. Next, we're going to change the bond distances. Here we have 3 buttons, which allows us to change the bond distance, the bond angle, and the torsion angles of a molecule. I click on the one for the bond distance. Now I go back to my molecule, select 2 atoms, and this window opens. Here, instead of the 1.0, we change it to 1.3 and click OK. You can see that this distance is now lower than the one of the other 2. We do the same for the other 2 distances. So we change all to 1.3. You can see that they are longer now. Next, we check the symmetry of our molecule. For this, we go to the tab Tools. We click Enable Point Group Symmetry and see that our current point group is C3b. And this is correct, so we can press OK. It's important to always check the symmetry of a molecule. Now we're ready to run an optimization. For this, we need to set up the commands that tell the program how to do the calculation. We go to Calculate, Gaussian Calculation Setup. Our job type is an optimization and frequency analysis. We need to choose the method. Per default, you will see Hartree Fock here, but this is not the one we're going to use. We will choose DFT, Density Function Theory, with B3LYP. The method B3LYP determines the type of approximations that are made in solving the Schrödinger equation. Now we had to set a basis set. This determines the accuracy. We choose 631G with DP. This basis set has a medium level of accuracy. We also have to add here some additional keywords. Integral equal grid equal ultrafine space POP equals brackets full comma NBO. And then give a job title here. Always make titles descriptive. Now we're ready to submit the job to Gaussian. We press Submit. Now you save the file. Always save it in the folder that you prepared previously. And then we submit the file to Gaussian. Please close the window of your not optimized molecule. There might be confusion otherwise later on. we now open the log file, and we also want to read the intermediate geometries this time. So this molecule looks quite similar to our previous one, but this is our optimized structure. To obtain general information about the job, we can click on the Results tab for a summary. This gives you all the key information about the calculations. It tells you the calculation type, method, the formula of your molecule, the basis set you chose, the charge you have, and very important is that you check if your molecule is actually optimized. And one way of doing this is to check the gradient. Here you will find the RMS gradient norm, and this number should be smaller than 0.0005. You also see here the symmetry, the point group. This is something we checked before submitting the job. We can now also check the real output, that is a file, a much longer file that Gaussian generates. This file is a pure text file. The following key information should be in your report. What is the molecule? What is the calculation method? What is the basis set? What is the final energy in atomic units? What is the RMS gradient? And what is the point group of your? Now we want to visualize our optimization. You remember we ticked the box Read Intermediate Geometries, and this is why we want to see the individual steps of the optimization. And you can visualize this by clicking on this green button here. It takes you through all the steps. As you can see, this happens fairly fast. If you want to go through the steps slower, just click here, step 1, 2, 3, 4, 5, 6, 7. So in this case, we have 7 steps for our optimization. We can also see this as a graph. If you go to Results, Optimization, there will be an optimization plot. You can pull this larger as well. The graph shows you the energy and gradient and how they have changed over the optimization. The first graph here gives you the energy of your molecule at each step of the optimization. The second graph gives you the gradient or slope of the energy versus R of your molecule at each step. And as you can see, we have 7 steps. We now want to animate the vibrations. From the main menu, we go again to Results, and then we choose Vibrations. Make sure the windows don't overlap so that you can see both windows at the same time. You should have 6 different frequencies here. We tick Show Displacement Vector. Now you can see some little arrows appeared. And if I press the green button Start Animation, you will see the molecule vibrating. We can go now through all the 6 different vibrations. Number 2. Number 3. All of these vibrations are active at 0 Kelvin. They represent the 0-point energy of the molecule, and this is a purely quantum mechanical property of the molecule. You can always turn and move your molecules so that you can see the vibrations best. In case you have any vibration with a negative number under the frequency heading, this means your molecule is not fully optimized, so you have to go back and repeat the optimization. Now we want to visualize the charges. When we solve the Schrödinger equation, the energy is not the only output, we also obtain a wave function. And the square of the wave function gives the electron density, which can then be partitioned up and assigned to each atom. The result is that we can determine an atomic charge. And we can also visualize this here. Go to Results, Charge Distribution, and a new window opens. We choose a type NBO. We want to color the atoms by charge, and you can also tell the program to show the numbers. We want to determine the energy for our reaction equation. We've done the ammonia molecule, but now we need to do the N2 and the H2. For this, we need to optimize the molecules. We open a new file, we go back to our periodic table, we choose the N, but this time we don't use the tetrahedral because we only have one other atom. I go back again, select now only the atom and add it here. So this is a linear molecule, and this is why we have to make sure we have a DH symmetry. And we run the Gaussian calculation as previously done. So now we can open our log file. We have read intermediate geometries. Open. Linear molecule detected, the warning. It's okay, we know it's a linear molecule. This time we had 4 optimization steps. So again, you can check the results as a quick summary. Always make sure your RMS gradient is lower than 0.0005. And you see the point of the symmetry, the infinity H is fine. And then we do the same for the hydrogen. Now we do the same for the hydrogen. Now that the job is finished, we can open the log file. We can read the intermediate geometries and see how many steps we had this time. So the optimization took 5 steps. Don't worry if there's no bond between your molecule. That is just a default by the program depending on the distance between the atoms. This is pretty fast, so I go through the steps slowly. Write down the results for this molecule. Check if the RMS gradient close enough to 0. Check if the RMS gradient is close enough to 0. Write down the energy. And now that we've done the H2, the N2, and the NH3, we have the energies of each of the molecules, and we can determine the energy for the reaction